And welcome to the next video in the Ampere series of videos. I just want to use this one to connect two concepts between the Lorentz Force Law, the first section of magnetism, and the Ampere's Law, the second section of magnetism. We will be using in this video both the first right-hand rule and the second right-hand rule. And so even though we don't have that much to cover, I do like to do this one slowly to make sure that everybody's clear about it. Now again, we're going to consider two current carrying wires. Last time we had two currents in opposite directions. There's no reason that nature forces us to do that. We could certainly have two wires with currents in the same direction. The last time, you may recall that what we did was we investigated the current the magnetic field due to the presence of both of these wires at some point in space, some point where air molecules are just sort of wandering by, right? But we want to investigate a new phenomenon, because you may remember that in the first section of magnetism, according to the Lorentz Force Law, you may remember that Lorentz demanded that the force on a current carrying wire per unit length was equal to the current in the wire times the magnetic field times the sine of the angle between the current and the magnetic field, right? You may also remember from Ampere's law that it demands that if you have a current that is appearing in one of your wires, that it forms a magnetic field in the vicinity of that wire, and the magnetic field, assuming that these are long enough to be considered infinite wires, is given by mu naught times that current that's in that wire over 2 pi times the distance away from the wire. So we're going to use both of these to investigate what happens to one wire due to the fact that another wire is actually nearby with a current. Well, the first thing that we need to do, we need to create a magnetic field using one of our currents, because in order for this to take effect, it actually has to be immersed in a magnetic field. So we need to create the magnetic field in order for that wire to experience the force. Okay, to avoid confusion, I think I'm going to relabel these as current 1 and current 2, because if I use current B, then I'm going to be confused by the magnetic field. So, okay, what we're going to do is we're going to ask, what is the force on wire 2 due to wire 1? So in order to do that, we have to first establish our magnetic field. So wire 1 makes a B field that we'll call B1, the magnetic field due to wire 1. And now remember, that's everywhere, but we're only going to think about where it is and its value in reference to wire 2. So what we're really interested in is, hey, what is that magnetic field over here at wire 2? Now the first thing that we're going to do is create our magnetic field lines. Remember, if you use your second right-hand rule, then that produces your B field around your wire, right? And your second right-hand rule indicates that the magnetic field should be in this direction, right? Which means that when the magnetic field encounters wire 2, it will be going into the board, into the screen. Okay, so we know that wire 1 creates a field B1, which will be equal to mu naught times current 1, because that's what's establishing our field, over 2 pi, and now we're interested in the distance between our two wires. So here we would say that this distance away from wire 1 to wire 2, r, is going to be equal to this number d, whatever that happens to be. Okay. Now that we established this, we can say wire 2 feels a force due to wire 1. So this one is going to be the force of wire 1 on wire 2 is going to be equal to, remember, this is given by this equation. Now actually we're going to put that as a force per unit length. The force per unit length of wire 1 on wire 2 should be given to as the current in wire 2, because that's the current that is responding to the magnetic field, times the B field from wire 1. Now here, if we have our wires parallel, we can consider sine theta is equal to 1. Now if you make your wires all kind of weird and twisty, that's not going to be the case anymore. In this class, we're going to focus on parallel wires for the case of the force between two wires. Okay. So what this does is it tells us that we can rewrite this force of wire 1 on wire 2 per unit length is equal to the current in wire 2 times B field 1 that we have already established, which is equal to mu naught I1 over 2 pi times the distance between the wires. Now this I2 here is considered a numerator term, so really what we can do is we can rewrite this as mu naught I1 I2 over 2 pi times the distance between our wires. Let's look at the kinds of forces that we're really going to be establishing here. So if we had a distance here, let's see what our distance is. So we can take a ruler and let's say we'll put these in, we'll presume these are centimeters. I think they're intended to be inches here, but so we'll say this is 3 centimeters, and these two are 3 centimeters apart. So let's label our distance is equal to 3 centimeters. Let's label our currents as I1 is equal to, let's put 12 amps in wire 1. Let's put 5 amps in wire 2. And what that's going to do is give us a calculation. The force of wire 1 on wire 2 per unit length, and this is a magnitude force, we can find the direction using our right hand rules, is going to be equal to, remember these will reduce to 2e to the negative 7 Tesla meters per ampere. I think I'm going to leave out the units for now, times our 12 amps times 5 amps, and that's divided by our distance of 0.03 meters, right? Because we're all in SI units here. And that is going to be equal to 4 times 10 to the negative 4 newtons for every meter of wire that you have encountering this magnetic field. Now, the really important thing that I want everybody to be clear about here is that this is not a matter of finding the magnetic field in between the wires or at a point P over here, that is an entirely different problem than the one that we have in front of us. If I give you two wires that are parallel, I could ask either of these questions. I could ask, hey, what is the force that's exerted here? Or I could ask, hey, what is the magnetic field that is present just in the air around these two wires? So that's two different situations that we're considering. Only one of those questions involves a force. Now that we have the magnitude of our force, let's find what the direction of our force is. I told you we'd use both right-hand rules. Now that we've already used the second right-hand rule in order to figure out what the direction of the magnetic field was, and we determined that to be into the page on this wire. So if we want to know what the direction of the force is, we resort back to the first right-hand rule. We know that the direction of current is upward, so we would point upward with our pointing finger. The magnetic field points into the page, so the middle finger points into the page, and that results in a force to the left. Now, you can go through this entire process to find out that the reciprocal effect occurs on wire 1 due to the presence of wire 2. And you would find then that there's an equal and opposite force inward on wire 1 due to the presence of wire 2. Or you could have already guessed that, perhaps, if you had considered Newton's laws. Newton's third law dictates that because this is wire 1 exerts a magnetic force F on wire 2 must also exert a magnetic force equal and opposite on wire 1. Now, as a summary here, you can, if I were to ask you, hey, what is the direction? You can actually, if you're one of those people that's really good at memorizing things, I'm not, but if you're one of those people that's good at memorizing things, you can remember that this is a little bit opposite of what you have with like positive and negative charges. Same currents will cause an attractive force. But if we were to reverse either one of these currents, you can work out that first right-hand rule again, and you would find that two parallel wires with opposite flowing currents will actually repel from one another. So if you can remember that, fine. If not, that's okay too. I always have trouble remembering that kind of thing, and I just sort of work through the right-hand rules to make sure that I don't get it wrong. Okay, please feel free to send me questions if you've got them. I know that this is a little bit on the tricky side. Good luck with it, and the next set of videos that I produce will be on the third segment of magnetism, which is Faraday's law.